Hello guys, welcome back in another video tutorial for microbiology with Hagnik. So today in this video tutorial we will going to do all the remaining things from allosteric regulation. So without any further delay, let's get started with the video. So the first topic that today we will going to learn is homotropic allosteric modulator as well as heterotropic allosteric modulator. Remember, homotropic allosteric modulator are those modulators that can act as a allosteric modulator as well as substrate. Okay, so that is the idea of homotropic allosteric modulator. Here substrate is acting both as a substrate as well as a allosteric modulator, and we have already discussed such type of example, that is the interaction between oxygen and hemoglobin, right? Because binding of oxygen on one subunit of hemoglobin increases the affinity of oxygen on the other active site of hemoglobin, right? Because we all know that hemoglobin is a multimeric protein, right? So on on binding of oxygen on one subunit of hemoglobin induces a conformational change in that particular subunit, that in turn increases the affinity of others subunit active site for that particular oxygen, right? So that is the idea of homotropic allosteric modulator. Now let's come to heterotropic allosteric modulator. Heterotropic allosteric modulator are the thing where modulator and substrates are different thing. That means here substrate is not playing the role of a allosteric modulator. We also know the example of heterotropic allosteric modulator, that is the interaction between 2,3-BPG and hemoglobin, right? Where binding of 2,3-BPG on one subunit of hemoglobin decreases the affinity of that oxygen from the other subunits of hemoglobin, right? So that is the idea of heterotropic allosteric modulator. So remember, homotropic allosteric modulator is most of the cases a activator. Okay, but heterotropic allosteric modulator is most of the cases can be both activator as well as inhibitor. Okay, so that is the idea of homotropic allosteric modulator and heterotropic allosteric modulator. So now let's move to the allostericity of aspartate transcarbamylase. So allostericity, before going to talk about the allostericity of aspartate transcarbamylase, I want to tell you that we have already discussed about this enzyme aspartate transcarbamylase. Try now, pause the video and try to think where we have discussed it. We have discussed it during the discussion of de novo synthesis of pyrimidine nucleotides, right? So it was the enzyme that converts carbamyl phosphate to carbamyl aspartate. That was the second step. Try to remember. So here aspartate was used up, right? And PI was released. So this is the enzyme aspartate transcarbamylase, and this enzyme is highly regulated by allosteric regulators. So now here we will going to talk about how aspartate transcarbamylase is allosterically regulated. So here what's happened, that CTP, that is cytidine triphosphate, and if you remember, then you may know that cytidine triphosphate was the end product of that pyrimidine nucleotide synthesis pathway. So here CTP will going to play the role of allosteric inhibitor, and ATP, which is a purine nucleotide, will going to play the role of a allosteric activator. Now try to think about this. Aspartate transcarbamylase will be allosterically inhibited when there will be a very high amount of pyrimidine nucleotide in the system, and that is also makes sense, right? Because if the cell have high amount of pyrimidine nucleotide, then why it will on the de novo pyrimidine nucleotide synthesis pathway, right? So that is the idea. So here in that case CTP will going to play the role of allosteric inhibitor, and it will going to block this enzyme aspartate transcarbamylase. Okay, and here when aspartate transcarbamylase needs to be allosterically activated, so the situation will be when in the system there will be high amount of purine nucleotide present. Now again try to think about this. If the cell has high amount of purine nucleotide, for example ATP, then cell also try to make the balance by increasing the production of pyrimidine, right? because the amount of purine and pyrimidine should be equal in amount, right? So under such circumstances, the ATP which are present in excess amount will going to activate aspartate transcarbamylase as a allosteric activator. Okay, so that is the idea of allostericity of aspartate transcarbamylase. So here you can find out negative allostericity in presence of CTP and positive allostericity in presence of ATP. And when CTP and ATP both are not present, the enzyme is showing a medium line. Okay, so that is the idea of allostericity of aspartate transcarbamylase. Here you can see this CTP, when it is present in excess amount, it will going to inhibit the enzyme responsible for this conversion, right? So that is the idea. So that is the idea of allosterism of aspartate transcarbamylase. Now let's talk about the Hill equation. So we are talking about allosteric enzymes, right? So they are the enzymes who have multiple subunits, right? And at least one of the subunit of the enzyme will going to have V0 versus substrate curve sigmoidal. Okay, rather than the hyperbolic curve which we used to say in case of Michaelis-Menten equation, right? So under such circumstances, we will going to see sigmoidal saturation kinetics instead of hyperbolic saturation kinetics. Okay, so here mainly two type of thing can happen. One is positive cooperativity, another one is negative cooperativity. So as I have told you that most of the allosteric enzymes are multimeric in nature. So what will going to happen here, along with the active site there will be another binding site in that particular enzyme. Okay, now most of the cases it will be a another binding site, not a active site, but in some cases the active site on one subunit may act as a allosteric site for other subunit. Meaning, let's say the active site which is present in this subunit may act as a binding site for this active site. Okay, so that is the idea. So positive cooperativity occurs when the binding of one allosteric regulator on one binding site or one active site will going to induce conformational changes in the other active site that will going to increase the affinity of the active site for the substrate. Meaning, if we going to try to simplify this, the idea is very simple. That is, let's go back to our hemoglobin example. So hemoglobin is multimeric subunit, we all know. So the idea is positive cooperativity occurs when one oxygen bind with one active site of the one subunit of the hemoglobin enzyme. Okay, and as a result, what will happen? This O2 will going to induce a conformational changes in the active site that will in turn increase the affinity for oxygen on the other active site of the enzyme. Okay, so that is the idea. And as a result, O2 can bind with the other active site very widely. So that is the idea, and that is what we call positive cooperativity. But in case of negative cooperativity, the things are different. So now we are talking about this type of cooperativity with hemoglobin example constantly. Now let's take a hypothetical example. Here we are considering that the allosteric modulator is Y. So what will going to happen that this enzyme, now let's say here this site will going to play the role of allosteric site and this site will going to act as a active site. So this is the allosteric modulator. Okay, now let's think about this, that it is a inhibitor. Okay, so what will happen when Y will bind with that allosteric site of the enzyme, it will going to decrease the affinity of the active site of the enzyme for the substrate. So that is the idea of negative cooperativity. Okay, so now here this type of sigmoidal saturation kinetics follow Hill equation. But before that, I want to told you that this cooperativity kind of thing is very common and it helps us to regulate the response of the enzyme to change in the concentration of the substrate. Meaning, for example, remember when positive cooperativity inducing moderators or when positive cooperativity inducing modulators are present, remember the enzyme will going to be highly sensitive for narrow change in the concentration of the substrate. Meaning, when oxygen is present at the binding site or allosteric site of the hemoglobin, a small change in the concentration of the oxygen can create a great impact in the working of enzyme. Similarly, in case of negative cooperativity, small change in the concentration of the substrate can make enzyme insensitive. Okay, so that is the idea. That means in case of negative cooperativity, meaning when let's say 2,3 BPG is present, the small change in concentration of oxygen will not going to create any significant change in the affinity of the active site of the enzyme. Okay, so that is the idea. So cooperativity also helps us to regulate the response of an enzyme to change in the concentration of the substrate. Okay, so now we will going to talk about the Hill equation. So if I going to explain you before going to enter the Hill equation about this thing or more easily, then I want to told you that cooperativity helps to regulate the response of enzyme to small change in the concentration of the substrate. We can understand this by the way, that is, when positive cooperativity inducing modulators are present in the binding site or allosteric site of the enzyme, remember this enzyme will going to be highly sensitive to small change in the concentration of the substrate. And as a result, if you going to decrease the amount of the substrate or if you going to increase the amount of the substrate, which will going to be a very small scale change, that particular enzyme will going to show you a great response. But when negative cooperativity inducing modulator are present, you may not find any kind of significant changes on small change in the substrate concentration when this enzyme is bounded with any kind of negative cooperativity inducing modulator. That is the idea. So now let's move to the Hill equation. So all the allosteric enzyme follow this equation instead of Michaelis Menten. That is theta is equal to L to the power n by Kd to the power n plus L to the power n. So here theta is the fraction of the ligand binding site filled or unfilled. That is the fraction of the site available or unavailable in the allosteric site of the enzyme. The concentration of the ligand, dissociation constant, and n is the Hill constant. And this n will going to describe you the concept of cooperativity, because if n, the value of n will going to be greater than 1, remember that particular enzymatic reaction will going to show you positive cooperativity. Now if again n is equal to 1, then you will exhibit or you will show equilibrium, or what I am telling, sorry for that, because when n greater than 1, the enzymatic reaction will going to show positive cooperativity. Okay, now when n is equal to 1, there will be no cooperativity shown, and we will going to see normal Michaelis Menten kinetics under such condition. But when n less than 1, we will going to see negative cooperativity. Okay, so that is the idea. So the value of n can be determined by number of the ligand binding site and strength of the cooperativity. Okay, so that is very very important. Now we can also take log on both the side, and we can modify the equation in such a way, that is log theta 1 by theta is equal to n log concentration of L minus n log Kd. Okay, so that is the Hill equation. So if we going to repeat the concept of Hill equation, so remember, as we have seen in case of normal enzyme that they are going to follow Michaelis Menten equation, just like that allosteric enzyme will going to follow Hill equation. Okay, where the equation is theta is equal to concentration of L to the power n Kd to the power n plus L to the power n. Here theta is the fraction of the ligand binding site filled or unfilled, L is the concentration of the ligand, Kd is the dissociation constant, and N is the Hill constant. So Hill constant describing us the cooperativity, and that is why it is very, very important. And we can determine the value of N by determining the number of the site available, that is number of the ligand binding site, and also the strength of the cooperativity. Okay, so if the value of N will going to be greater than 1, it will going to show positive cooperativity. Positive cooperativity, what is the meaning of positive cooperativity? I have already told you, that is the binding of allosteric modulator at the allosteric site of the enzyme will going to change the substrate binding site in such a way that will going to show a high affinity for that particular substrate, right? And if the value of N will going to be 1, then here we will not going to show, or we will not going to see any kind of cooperativity. But when N, the value of N become less than 1, we will going to see negative cooperativity. Okay, and here negative cooperativity means binding of allosteric modulator on the allosteric site of the enzyme will going to induce a conformational changes in the substrate binding site in such a way that the binding site will going to have less affinity for that particular substrate. That is what we call negative cooperativity. Okay, so that is the idea of our Hill equation. Now here we have modified the Hill equation by taking log on the both side. So that is the different thing. So that is the idea of our Hill equation. So I hope this video will be helpful for you for understanding the concept of allosteric regulation. So this is for today's video. So thank you.